All right, guys, so what we're going to be doing here is introducing ourselves to just basic probability, and you're going to get a little taste of the different types of probability we're going to talk about in this unit. Before we start, though, I'm just going to give the basic formula, the overall formula for determining the probability of a single event, just so that we can use this throughout the notes today. All right, so you'll want to write this down, but basically if I'm trying to find the probability of any event, it's going to be the number of desired outcomes divided by the number of possible outcomes. So in this case, we're talking about some event A, could be anything, right? It could be the probability of selecting a person with red hair from an audience, or the probability of flipping heads on a coin, right? So whatever your event is, you'll calculate that probability by taking the number of desired outcomes, which is whatever it is you're trying to find, the thing you're hoping happens, out of the number of possible outcomes, so divided by the total number of things that could happen. And we'll see that in action here with some basic examples. So if a fair coin is flipped, what is the likelihood that it comes up heads? And what we're investigating here is just the probability of heads, let's say. So if we use this little formula, if you flip a coin, how many opportunities do you have to get the desired outcome? Well, heads is only on one side of the coin, so you only have one chance at that when you flip a coin. But how many possible outcomes are there? Well, there's heads and there's tails, so there are two possible outcomes. So you could say that the probability of flipping heads is 1/2, or 50%, right? Or 0.5. All are okay ways to say that the probability of heads is half. Half the time you'll get heads. All right, let's take a look at the six-sided die. Pretty common to involve dice, coins, spinners, all these things. So a six-sided die is rolled. How likely is it that the number rolled is greater than 2? So what we're trying to find here, if I want to give some notation, is that I want to find the probability of a number that is greater than 2. And I'm just going to make a list to myself over here of all the possibilities. I could get a 1, I could get a 2, a 3, a 4, a 5, or a 6 when I roll a six-sided die. And of these possibilities, of which there are 6, there are 1, 2, 3, 4 of them that are greater than 2. So my probability would be 4/6, but I wouldn't leave it like that. I would leave it as 2/3. Or if you were to write it as a percent, you could write it as approximately 67%, or approximately 0.67, or 0.6 repeating. So I am trying to communicate to you that you can write these probabilities as fractions, percentages, decimals. As long as they're all accurate, you can do that. Okay, most often you probably hear probability presented as a percent, and that's fine as long as it's accurate. In this case, I probably wouldn't want to write this on a test because I could present this exactly as 2/3 or exactly as 0.6 repeating. A person is selected at random from this room. What do you think the probability is that they would consider themselves a cat person as opposed to a dog person? Okay, so this is a discussion that we have to have here, and I'd like you in the room to figure this out. It'd be good if you had this data. So what we're trying to figure out, first of all, is the theoretical probability, because it says, what do you think? This is a guess. So our theoretical probability might be the probability of cat person, and I'm just going to guess. I'm going to guess that the probability of picking a cat person out of a random group of people is maybe 15%. Okay, that's just my guess, and that could be written as 0.15, all right? That could be written as 1/1500, so you could reduce, right? So there are different ways to write this, but how could we find this out for sure? You're going to actually have to run this experiment. And so I'm going to check, make sure your notes are done here because you're going to upload them. I want to see this data, and all you need to do is everybody in the room needs to say whether they're a dog person or a cat person. Feel free to use the whiteboard to organize this. Somebody should probably take charge and organize this data. But what you're going to do to find out for sure is to calculate the exact probability of C. The number of possible outcomes in this case is just the number of people in the room. Now, if everyone's in the room, there are 24 students. and the substitute teacher, who you could definitely include in this study as well, because more data is better. So it's possible that that number of people is 25. If there are people who are absent, then it's less than that. And then up here, that's going to be the number of cat people in the room. And in case it's unclear, a cat person is just a person who prefers cats to dogs. You do have to choose. You can't be like a squirrel person or something. It's got to be cat or dog. All right. So you do need to run this experiment. You'll have this data, and then you're going to compare that to your guess. My guess is 15%. Yours could be anything, but you're comparing your theoretical probability to your experimental probability, which is something that we're going to do a lot in this unit. All right, so it wouldn't be a bad thing to write down a general definition of the difference between these two things, because that's going to be a recurring theme in this unit. Combinatorial probability is not something you're going to see a lot of, but the reason I want to go over it is because it's a good exercise in logic and organizing your thoughts. So let's say a fair coin is flipped 4 times consecutively, and we want to know the probability of flipping exactly 2 heads. So I'm going to flip a fair coin once, and I'm either going to get heads or tails, right? And then I'm going to flip it 3 more times, and I want to know, of all of those outcomes, what's the probability that 2 of the 4 flips were heads? And you might say 50-50, right? 2 out of 4, you're going to get a 50-50 chance of any of these outcomes. Well, what we're going to do to actually figure this out is we're going to make something called a tree diagram. And that's going to outline all of the possibilities. So anytime you have an event happening and then another event happening, it's good to have a tree diagram to model the situation. So in this situation, we're starting from, I'm just going to draw this little dot here. It's called a node, but it's just going to represent the very first situation in our trial. And a coin is flipped, and we know that when a coin is flipped, there are 2 things that can happen. You could either get heads or you could get tails. So that's the first coin flip. Now, regardless of what happens here, I'm either going to be in a position where I just flipped heads or I just flipped tails, but I'm going to flip again. So when I flip again, I could get heads or I could get tails. If I had gotten tails, that wouldn't change, right? I could flip again and still get heads or still get tails. So what this diagram is starting to show us is all of the possibilities for how this game can play itself out. Now at this point, we've only flipped a coin twice. This was the first coin flip, and one of these was the second coin flip. Depends on what happened in the first coin flip, right? We do have this coin being flipped 4 times, so we have another flip that we've got to model here. Regardless of what happened, any of these could result in heads or tails, so I'm going to draw one more row of the tree diagram. Okay, so hopefully yours looks like mine. That's after our third flip. And so you're starting to notice that the way that we've labeled this is useful, because if I look at this node, and again, I've only flipped it 3 times, I need to flip it 4 times. This node is showing us the situation where we flipped heads, heads, and then heads again. This node here is a situation where we flipped heads, heads, and then tails. This would be heads, tail, heads. This is heads, tails, 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 heads, heads, right? So you're seeing all of the possibilities here laid out. I'm going to draw the 4th row of branches here. So when your diagram is done, what you should do to see the possibilities is you should write out what these outcomes actually are, because this outcome is heads, 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 4 heads in a row. This outcome is heads, 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 tails. This should be heads, heads, tails, heads, 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 tails, tails. So go ahead and write out all the outcomes beneath all of those branches, and then we'll talk about what the probability is of actually getting this desired outcome. Okay? So we're going to find the probability now of flipping exactly 2 heads. So the probability of exactly 2 heads. So what is the number of possible outcomes? Well, it's however many branches we ended up with here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yes, there would be a logical way to calculate that, but we're just looking at our tree diagram here. So of those 16 possible outcomes, let's find all the outcomes that actually had the desired outcome that we wanted. So exactly 2 heads. That would not be this. There's 3 heads here, 3 heads here. There are 2 heads there, so this would be one of those outcomes. We've got another one here with exactly 2 heads, and another one there with exactly 2 heads. It looks like we've got one here, and here, and here as well. So while it might have seemed initially like 2 out of 4 heads is going to be 50% of the time, it turns out that in this case, there are only 6 of these outcomes where you get 2 heads. And hopefully we can all agree that each of these are equally probable. It's equally as likely that you'll get any one of these outcomes because at every node, there's a 50% chance of flipping heads or tails, unless you're playing with an unfair coin, but we're playing with a fair coin. So I would present this probability as 3/8, which is not what we would have expected. And in this next exercise, I think we are going to move away from that and talk about these next week. So we'll press pause on that example here and go ahead and turn your paper over to the back. All right, this is the last thing that we're going to do in this video, and I'm not going to give you the answers. It's, again, an exercise I want you to do as a class and see if you can figure out how to calculate this here. We're going to talk about this conditional probability scenario, and we're not going to do the bottom question or the independence of events question. We're going to talk about this when we do our lesson on independent events. We did the bottom question yesterday. But when we talk about conditional probability, something about the question changes, and I want you to see if you can figure out what that is. So a person is selected at random from this room. So again, in this room, you still have the same amount of people you had when you were calculating the probability earlier. What is the probability of selecting a dog person, given that they have siblings? So this is where it gets a little more complicated. I want to know the probability of selecting a dog person, given that they have siblings. Given meaning that's the most important thing. We're picking from that group of people. Okay? So if it's given that I'm going to pick a person who has siblings, then what's the probability of that group I will pick a dog person? And that's a calculation you can all do as a group, figure out how to calculate it, and then I want to see how it ended up tomorrow before we start our lesson. Okay? So that does it for this introductory lesson. And the things we didn't fill in here, we will fill in as the unit goes on. But remember, finish this and then upload it into Classroom so that I can see that today went well for you guys.